Good morning. My name is Tobert Cavalli, and this is my MK7 ARRESTOR Systems Controls project. It mainly focuses on the comparison between the fixed and tunable gap dynamics mechanisms. The objective of this project was to demonstrate a control model for an aircraft arresting system using a tunable fluid. And basically, the project focuses on modeling and comparing two types of aircraft arresting systems, and I did this using Simulink. Those two systems are the MK7 fixed gap system and the AAG tunable gap system, and the goal was to simulate how both those systems decelerate two different aircrafts, a heavy F-18 fighter jet and a lightweight UAV aircraft. And we use those two to analyze how effective each system is under different conditions. And to do this project, I began by modeling the MK7 system, which uses a fixed mechanical damping setup. And this is the model that I made in Simulink. And this Simulink model basically shows both the F-18 and the UAV added together by applying different gains to get the correct acceleration or the deceleration outputs. And I did this by applying the respective velocities and integrating the velocity and the position to get the desired outputs for the desired scope outputs. These are the scope outputs that I got, and basically the first graph compares the velocity and time for both the F-18 in blue, as you can see here, and the UAV in yellow. We saw in this graph using the MK7 system that the F-18 decelerates quicker than the UAV model, and this is problematic because UAVs are lighter aircraft. So in this second graph, we can see the acceleration time graph for both aircrafts. The UAV is more responsive to arresting time, achieving quicker stabilization, while the F-18 decelerates more quickly and smoothly over a longer period. This is problematic, and to address this, we developed a tunable gap system model based on the AAG concept. And this is the tunable gap model that I developed. And as you can see, it's not that much different in terms of the block diagrams. The only difference was in the gains that I integrated for this specific model. Basically, unlike the MK7 system, the AAG system dynamically adjusts braking force based on aircraft speed and mass, and that is what I used. That is what I used after doing the hand calculations to determine the correct gains to put in this model to get the desired outputs. And these are the results of the tunable AAG system. And that simulation showed that the AAG system is far more adaptive. The F-18 experienced longer but smoother deceleration, as you can see here and here, while the UAV was arrested quickly without excess force. So unlike the first graph, you can see that the UAV is arrested quickly because it's lighter, and that makes more sense because we can determine variable weight. We can determine variable weights and use those to determine variable decelerations. So in conclusion, I determined that a tunable system like the AAG outperforms a fixed system like the MK7 by enabling precision arrests across diverse aircraft types, ensuring safe and more flexible carrier operations. And these are the differences and the benefits between the fixed and the tunable model. The fixed model is good for larger aircraft and heavier aircraft, and it uses a constant because it uses constant mechanical properties. It cannot adapt to different aircraft weights and speeds. But as we saw in the tunable system, it employs a real-time control system where it adjusts its braking force, and it can accommodate a wide range of aircrafts from UAVs to heavy fighter jets. So I also implemented an L custom function, a custom L function subsystem in Simulink, and this subsystem dynamically calculates the braking gap, which is based on velocity and desired deceleration, and the output graph for this showed a decreasing trend representing an increasing deceleration over time, which is consistent with real-time control behavior, as we're going to see in the next slide. And here you can see what I'm talking about. The blue graph, the blue curve here, which is the product curve, decreases linearly with time, which suggests that the L function is producing a linearly increasing deceleration. And this behavior is typically typical like when a constant force is applied to an object with increasing resistance or effective inertia. In short, this graph illustrates that under a constant control input in yellow, as seen here, the system's acceleration continuously becomes more negative, which indicates a growing deceleration. In conclusion, this project successfully modeled and analyzed the dynamics of an aircraft deceleration using both the MK7 and the AAG arresting systems, with a focus on comparing performance between an F-18 fighter jet and a UAV. And we did this by developing Simulink block diagrams as you've seen before, which incorporated velocity and position integrators that helped us get the correct acceleration, velocity, and position outputs that we needed. And basically, this project demonstrates that while the MK7 fixed gap system is simple and reliable for single aircraft types, the AAG tunable system offers a greater flexibility for a wide range of aircraft. And yes, this is my project. Please feel free to ask any questions in the comment section. Thank you for watching.